In Chapter 7, we're looking at rational expressions and functions. In Section 7.1, Rational Expressions and Functions, Multiplying and Dividing, our objectives are to define rational expressions, define rational functions and describe their domains, write rational expressions in lowest terms, multiply rational expressions, find reciprocals for rational expressions, and divide rational expressions. Defining rational expressions. In arithmetic, a rational number is the quotient of two integers with the denominator not zero. An example of a rational number is 2/5. A rational expression is an algebraic fraction. It's the quotient of two polynomials also with a denominator not equal to zero. Rational expressions are the elements of the set P over Q, where P and Q are both polynomials, and Q, the denominator, cannot equal zero. Here are some examples. 3 divided by 2m is an example of a rational expression. We have polynomials of 3 and 2m, and the denominator 2m cannot equal 0. The second one is also an example, x divided by x minus 5, as well as the third example here, 2b squared minus 4b plus 3, all divided by 2b minus 7. A rational function has the form of f of x, which is equal to a p of x polynomial in the numerator and a q of x polynomial in the denominator, where the denominator polynomial cannot equal 0. The domain of the rational function includes all the real numbers except those that make the denominator polynomial q of x equal to 0. The graph of the function f of x is shown at the right. The domain of this function is all the real numbers except x equals 3, where f of x is not defined. Our function has a polynomial of 2 in the numerator and a polynomial of x minus 3 in the denominator. So the domain is all real numbers except for what would make the denominator equal 0. So we can say that x minus 3 cannot equal 0. And if we were to solve this as an equation by adding 3 to both sides, we could see, using the same symbols here, is that x cannot equal 3. So the x, or the input values, can be any other real number except where x is equal to 3. And the corresponding graph will indicate that breakup in the domain of positive 3. The function does not exist where x is equal to 3. And the behavior of the graph as you get close to x equals 3 is asymptotic. In other words, it's going to approach either positive or negative infinity as the x values get closer to 3. For these examples, we're looking at each rational function and finding all the numbers that are not in the domain. Then give the domain using set builder notation. So our first function, rational function, is f of x equals 7x divided by x squared plus 9. The domain is all the real numbers except what values of x would make the denominator equal to 0. The denominator in this case is x squared plus 9, and we want to know if there's any possible values of x that would make this equal to 0. So we could say x squared plus 9 cannot equal 0. Well, there are no restrictions in this case because there are no values of x, which if you squared them would be positive or 0, and adding another positive 9 would never equal a 0. So there we say that there's no restrictions, and we can also say that the domain is all real numbers. And using the set builder notation, we can write this as the domain is x such that x is a real number. So really any real number is part of the domain. There are no restrictions. Let's look at g of x. In g of x, our numerator is 3x squared minus 9x plus 5, and the denominator is negative 5. Again, we say that this has no restrictions here because there's no possible values of x that would make the denominator equal to 0. So we can use the same set builder notation here. The domain is all the x such that x is a real number. Now h of x is a rational function with the numerator of x plus 4 and the denominator of x squared plus x minus 20. There are restrictions in this for the domain of this rational function. And the restrictions would be whatever values of x would make the denominator equal to 0. So we can say that x squared plus x minus 20, the denominator, cannot equal 0. And this is similar to a polynomial equation that can be solved using the factoring technique by finding the factors of negative 20 that will add up to the middle coefficient of positive 1. Well, that would be a negative 4 and a positive 5. This can be factored, the denominator can be factored into x minus 4 and x plus 5. So we want to know what values of x that would make it the denominator equal to 0, and that would be a restriction. So we want to know where those factors will not equal 0. We can set each one of those using that 0 factor property, saying x minus 4 cannot equal 0. If it's equal to 0, then that factor is 0 and the whole denominator is 0. So by solving that for x, we say that x cannot equal 4. That is a restriction on the domain. Similarly, with the second factor of x plus 5, we say x plus 5 cannot equal 0. So x cannot equal negative 5. Every other value of x will be true for this, will be part of the domain of this rational function, except for those two values of x. And we could say, using set builder notation, that the domain is all the x values such that x is any number except 4 and negative 5. So we can say x cannot equal 4 and x cannot equal negative 5. The fundamental property of rational numbers: if a over b is a rational number and if c is any non-zero real number, then a over b is equivalent to a times c over b times c. When you're dealing with fractions, you can always find equivalent fractions by multiplying the numerator and the denominator. For example, you have the fraction 3 over 7. What you could do is find an equivalent fraction by taking the numerator and the denominator and multiplying by the same value. So you can take 3/7 and multiply the numerator by, say, 2, as long as you multiply the denominator by 2. You would get an equivalent fraction, which would be 3 times 2 of 6 over 7 times 2 of 14. So this is considered to be the fundamental property of rational numbers. When you're dealing with examples later on in this section, whenever you're multiplying the numerator by something, you also want to multiply the denominator. Writing a rational expression in lowest terms. Step number 1, we're going to factor both the numerator and the denominator to find their greatest common factor and apply the fundamental property. We can simplify these rational functions by finding greatest common factors and dividing out those greatest common factors. Let's look at these examples. Write each rational expression in lowest terms. For part A, we have 12c squared divided by 16c. The greatest common factor of the numerator and the denominator can be found by looking at the coefficients 12 and 16. The largest number that goes into both of those is 4. And looking at the fact that the numerator and the denominator both have a c, the greatest common factor is the lowest exponent. So 4c is the greatest common factor of both the numerator and the denominator. Now what you could do is write the numerator as that greatest common factor, 4c times 3c, and that would give you 12c squared. The denominator can also be written as 4c times 4. So those common factors of 4c can divide out, and the rational expression can be expressed in lowest terms as 3c divided by 4. So when you're looking at rational expressions, let's write it again over here, 12c squared over 16c, you can simplify the rational expression by factoring out those greatest common factors. In part B, we have 8 minus m divided by 2. Now the greatest common factor of the numerator and the denominator is 1. There is no other common factor. In order for 2 to be a common factor, it must be a factor of both terms in the numerator. So this has no other greatest common factor other than 1. So the result is already expressed in lowest terms. We say that this cannot be simplified any further. All right, let's look at part C. We want to simplify the rational expression, writing it in lowest terms, by determining if there's any greatest common factor. Well, in part C, we need to factor before we determine what the greatest common factor is. The numerator can be factored. Notice that there is a common factor of 5 just in the numerator. So if we factor out that common factor in the numerator of 5, the remaining factor is x plus y. Now the denominator can be factored as well. You should recognize that as a difference of squares that can be factored as x plus y and x minus y. Now looking at both the numerator and the denominator together, we see we have a greatest common factor of both terms, the x plus y. So that x plus y can be divided out of both of those terms, crossing it out of the numerator and the denominator, and then simplifying the result so that you have a 5 in the numerator and a factor of x minus y in the denominator. The only way you can divide anything out of a fraction or cancel anything out is if the entire quantity is next to a multiplication or division. You cannot cross anything out if it's next to a plus or a minus sign. All right, part D, we want to write each rational expression in lowest terms. We want to find the greatest common factor, but before we find the greatest common factor, we need to factor both the numerator and the denominator. The numerator is a trinomial, and looking at the fact that it's a simple trinomial, finding factors of negative 15 that will add up to 2. The factors of the numerator can be expressed as z plus 5 and z minus 3. The factors of negative 15 that will add up to 2 are positive 5 and negative 3. So our numerator is in factored form. The denominator should also be in factored form. The greatest common factor of the denominator is 7. So you can factor a 7 out of the denominator, and the remaining factor would be z minus 3. Now notice that we have a common factor in the numerator of z minus 5, and in the denominator, z minus 3, and the denominator also has that factor. So that's the greatest common factor that can be divided out of both the numerator and the denominator. The resulting expression can be written as a rational expression using z plus 5 in the numerator and 7 in the denominator. Now let's look at part E. We have a polynomial in the numerator that has 4 terms and a polynomial in the denominator that has 4 terms. So the factoring by grouping method is a good approach. Let's look at the numerator to begin with. The greatest common factor of x squared plus xy is x. So if you factor out an x from the first 2 terms in the numerator, dividing out that x, you get x plus y. Now let's look at the last 2 terms in the numerator. The greatest common factor here, both terms have the z, and because that's a minus sign here, we can factor out a minus z. And the remaining factor, when dividing out that negative z, is going to be x plus y. The denominator can be factored as well. Also, noticing that it has 4 terms, we'll try the factor by grouping method. Looking at the first 2 terms in the denominator, there is a common factor of a. So if you factor out that common factor of a, the remaining factor would be x minus z. The last 2 terms in the denominator have a common factor of b. So you can factor out a plus b, again, since the sign is a plus there. And the remaining factor, when factoring out the b, you get x minus z. Now let's look at the entire numerator. The larger groups in the numerator have that common factor of x plus y. So if you factor out that common factor of x plus y, then what is left in front is the x minus z. So that would be your other factor. Now let's look in the denominator. Notice that the common factor of x minus z is in both of the larger groups. So our one factor would be x minus z. With the other factor, what's left out in front, when you factor out that common factor of x minus z, we get a plus b. Now, if there's any greatest common factors in the numerator and the denominator, if any of those factors are the same, we can divide those out to simplify the rational expression. Notice we have an x minus z as a factor in the numerator and an x minus z factor in the denominator. Since those factors are exactly the same and they're next to multiplication, we can divide those out, and the result is a rational expression where the numerator has the factor x plus y and the denominator has the factor a plus b. That is our rational expression in lowest terms. In part A for this slide, we have the a minus b and b minus a. Now the b minus a can be expressed in another way. We can write the numerator as a minus b, and the denominator, by rearranging the terms, you have a negative a plus b. Now it's often we can factor out, if the leading coefficient is negative, we can factor out a negative from the terms, leaving the numerator as a minus b, and the denominator, if you factor out a negative 1 from the denominator, then your remaining factor is a minus b. Now we can see that the numerator has a factor of a minus b and the denominator has a factor of a minus b as well as this negative 1. With this common factor, greatest common factor of a minus b appearing in both the numerator and the denominator, we can simplify this result by dividing out, but don't forget that negative 1. We could write this as 1 over negative 1, which simplifies to negative 1. So that a minus b over b minus a can be written by factoring out a negative from the denominator. We can write this and see that we have a greatest common factor in both the numerator and the denominator. Let's look at part B. In part B, we have the polynomial x squared minus y squared. And you should recognize that as a difference of 2 squares that could be factored into the form of x plus y and x minus y. The denominator is y cubed minus x cubed. That's one of those special trinomials, special difference of cubes that can be factored into a binomial and a trinomial. The binomial factor would be y minus x, and the trinomial factor would be y squared plus xy and plus x squared. So now that the numerator and the denominator are in factored form, we want to determine if there's any greatest common factor. Now what we'll see here is they're not any exactly the same factors, but we do notice that the numerator has a factor of x minus y, and the denominator has a factor of y minus x. And that's x minus y in the numerator and a y minus x in the denominator. That is very similar to this problem that we just did in part A. If you factor out that negative from the denominator, you will end up with a result that looks like this as follows. The numerator is x plus y, x minus y. If you factor out a negative from that first factor of y minus x, you get negative x minus y, and then y squared plus xy plus x squared. Now we see that we have these two common factors of x minus y that can be simplified, and we have a negative out in front here. We can leave that as a negative out in front of the rational expression with x plus y in the numerator and y squared plus xy plus x squared in the denominator. That minus out in front can also be written in the numerator. And that would be our answer in simplified form, in lowest form. When the numerator and the denominator are opposites, in general, if the numerator and the denominator of a rational expression are opposite, the expression equals -1. That takes us back to the two previous examples where we had a minus b over b minus a. These are opposites, so we can say that simplified to a -1. Additionally, in the second example on the last page, we had an x minus y factor and a y minus x factor, and that simplifies to -1. When we are multiplying rational expressions, we want to follow these 4 steps. We're going to factor all the numerators and the denominators as completely as possible. We're going to apply the fundamental property. If there's any greatest common factors, we will simplify those. Step number 3 is to multiply the remaining factors in the numerator and the remaining factors in the denominator. Now, this note here is to leave the denominator in factored form. And then step number 4 is check to be sure the product is in lowest terms. For example, part A, we have x plus 1 squared times the rational expression x over x plus 1. We want to make sure that both rational expressions are completely factored, and we have that is the case here. The x plus 1 to the second power, we can write that as a rational expression over 1, and the second rational expression can be written as x over x plus 1. We do see a greatest common factor of the numerator. We have this x plus 1 factor. The denominator, we also have an x plus 1. The power of 2 here will allow us to reduce that. So we write this as a single rational expression, x plus 1 squared times x, and the denominator, multiply the denominator to get x plus 1. Now we're going to simplify the x plus 1 squares. Since there's 2 of them in the numerator, when we divide out, we'll divide out with 1 in the numerator. So we end up with an x plus 1 in the numerator and an x, and then that x plus 1 in the denominator will cancel out with one of those x plus 1s in the numerator. This is our answer simplified. Let's look at part B. We have a plus 2 over a plus 1. This first rational expression cannot be factored further, so we can write it as a plus 2 times a plus 1. The numerator of the second rational expression, a squared minus 1, that's the difference of 2 squares. So remember, it's x squared minus y squared. The two factors are x plus y and x minus y. So in this case, our x is a and our y is 1. So the two factors are a plus 1 and a minus 1. The denominator is also a difference of 2 squares that can be factored into a plus 2 and a minus 2. Now when we multiply these, we get a plus 2 factor times a plus 1 times a minus 1 in the numerator. In the denominator, we have an a plus 1, an a plus 2, and an a minus 2. We want to know if there's any common factors, the greatest common factor of the numerator and the denominator. We have an a plus 1 factor in the numerator that will divide out with an a plus 1 factor in the denominator. We have an a plus 2 factor in the numerator that will divide out with an a plus 2 factor in the denominator. So our result can be written as the remaining factors of a minus 1 in the numerator and a minus 2 in the denominator. All right, let's multiply m squared minus m minus 2 over 2m minus 6 times m minus 3 over m cubed minus 8. Our first step is to completely factor all numerators and denominators. In the first numerator, we have a simple trinomial. So we're looking at the factors of negative 2 that will add up to negative 1. And those factors are m minus 2 and m plus 1. The denominator of 2m minus 6 has a common factor, a greatest common factor of 2. If we factor out the 2, we're left with m minus 3. The numerator in the second rational expression is m minus 3, which is already as in factored form. The denominator is a difference of 2 cubes. So we can factor this as, remember the formula for x cubed minus y cubed. So our factors here, our x is m and our y is 2. 8 is the same thing as 2 cubed. So we can write this as m minus 2 as the binomial factor and m squared plus 2m plus 4 as the trinomial factor. Now when we multiply all of these, we can divide out any common factors that we see in the numerator and the denominator. We do have an m minus 2 factor in the numerator that can divide out with an m minus 2 factor in the denominator. We also have an m minus 3 factor in the numerator that can divide out with an m minus 3 factor in the denominator. So we can write what's left over after the simplifying. We can write it as m plus 1 in the numerator and 2 times the quantity of m squared plus 2m plus 4 in the denominator. And that is our answer in factored form. Finding the reciprocal of a rational expression. To find the reciprocal of a non-zero rational expression, you interchange the numerator and the denominator of the expression. When you're dividing rational expressions, or dividing one fraction by another fraction, you want to multiply the first by the reciprocal of the second. Remember when you're multiplying fractions such as 2/3 and dividing a fraction by another fraction, say 4/5, the way you divide fractions is to change it to a multiplication problem. So you keep the first fraction as 2/3, but you change the division to multiplication and you write the reciprocal of 4/5, and that is 5/4. And then you can multiply the numerators and the denominators to get 10/12, which reduces to 5/6. So what we're looking for here is when we're dividing rational expressions with variables, whenever you have a division problem, you change it to a multiplication and you write the reciprocal. In part A, we're taking 2z over 9 divided by 5z squared over 18. We're going to change this to a multiplication problem. The first term, 2z over 9, change the division to the multiplication and write the reciprocal, 18 over 5z squared. This can be simplified. We do have a common factor of z in the numerator and a common factor of z in the denominator. Although there's a z squared, that's going to simplify. We also have a common factor of 9 in the numerator that can simplify with the 18 in the denominator. What we'll end up with is 2z times 18 in the numerator and 9 times 5z squared in the denominator. By simplifying those z's and that 9 that goes into 18, 9 goes into 18 2 times. So in the numerator, this will be 2z times 2, but that z will divide out with a z on the denominator. So we'll end up with 4 in the numerator over 5z in the denominator. Part B, we have 8k minus 16 over 3k divided by 3k minus 6 over 4k squared. Let's write the first one in factored form. The common factor of the numerator is 8, and then we'll have k minus 2 over 3k. We're going to change the division sign to a multiplication and write the reciprocal, 4k squared in the numerator and 3k minus 6 in the denominator. Now, this denominator actually can be simplified. The greatest common factor of 3k minus 6 is a common factor of 3, and when you divide out that 3, you'll get k minus 2. Now notice that we have a common factor of k minus 2 in the numerator and a k minus 2 in the denominator. And let's see what we get when we multiply the numerators together. 8 times 4k squared. We can write that as 32k squared, and 3k times 3 in the denominator is 9k. There's a greatest common factor of k in the numerator and the denominator. So one of those k's of the k squared in the numerator will divide out with one of those k's in the k squared in the denominator. So we can end up with 32k over 9 as our simplified rational expression. In this example, we're taking the trinomial x squared plus 3x plus 2 divided by x to the fourth divided by x squared plus 2x plus 1. The numerators are both simple trinomials, so we can factor those. First, the factors of 2 that will add up to 3 are x plus 2 and x plus 1 over x to the fourth divided by the factors of 1 that add up to 2 are x plus 1 times x plus 1 all over x squared. This is a division problem. We're going to change the division to multiplication and write this as the first fraction remains the same, and we change the division to multiplication, and the second fraction we write as the reciprocal. Now, let's see if there's any common factors in the numerator and the denominator. We have an x plus 1 factor in the numerator that will divide out with an x plus 1 factor in the denominator. We also have an x squared in the numerator that will simplify with that x to the fourth in the denominator. We have the x squared will divide out with the x to the fourth in the denominator, and that will leave an x squared in the denominator. Our result here will be a single fraction, and the numerator has an x plus 2, and the denominator has an x squared and an x plus 1 factor. This is our answer in factored form.